Hello everyone, this is Lab 2 Equipotential line and electric field mapping. So the target of this lab session is to investigate the relationship between the electric field and the equipotential lines. So our target was to map the electric field lines based on the detection of equipotential lines. So before sending or watching the experimental videos, I prepared this presentation or this video to explain the theory behind this lab. We have already studied the electric field in the first two chapters of the 201 course. We did not start the equipotential surface or the potential energy part. So that's why I will talk about the basic knowledge or basics of these topics to get you understand or to be able to understand the relationship between these two topics and the idea behind this lab. So let's start, or before starting, so our objective is to learn the concepts of electric field and equipotential lines using an experimental procedure to map the equipotential lines, and based on the mapping or the prediction of this equipotential lines, we will obtain the field lines. So let's start by the electric field. You all know what is the definition of a field, and which is defined by how an object interacts with another object. So a familiar example is the gravitational field. As we know, every point in space near the Earth has an associated gravitational field vector G. So if we consider a body of mass m and F is the gravitational force, okay, or the weight acting on it, so G is given by the ratio or the force per mass. So it's the force divided by the mass. As you can see here, the gravitational force is directed downward, and the direction of the gravity it's always also downward. Now similarly, we will consider a charge now. So the space surrounding a charged object is also affected by this object. We define what we call the electric field here. So as we have gravitational force, we have electric force, we have a electric field. So the electric field is also a vector, and it's produced by the charge. So unlike the gravitational field, the electric field direction depends on the sign of the charge. Let's consider a test charge. The concept of a test charge is to take a positive and a small charge. Why we are taking a small charge? Because we don't want to affect the charge distribution. We only need to detect the electric field. So the relationship between, similar to the relationship between gravity force and the mass of the object, we have a relationship between the electric field, the force, the electrostatic force, and the test charge Q0. So F equals Q times E. As you can see, F is a vector, Q is a vector. Do we know anything about the direction of these two vectors? Do they have the same direction? In fact, it depends on the sign of Q. So unlike the gravitational study, S and G, they have the same, the gravitational force and the gravity or the gravitational field, they have the same direction, while for the electrostatic force and the electric field, all depends on the sign of Q, because as you know, we can have a positive charge or a negative charge. A quick reminder regarding the electrostatic force. How to calculate the electrostatic force? Using Coulomb's law, which is K, Coulomb's constant, times Q times Q0 over R squared, the distance separating the two charges. R with a hat is the position vector. So the electric field is Fe, the electrostatic force, divided by the test charge Q0. So to know the direction of the electric field, we need to check the sign of the charge, okay, the sign of Q. So as you can see here, we have a positive charge. Let's take example A. So we have a positive charge Q, and we have our test charge Q0. So in this case, we know that if we have two charges with the same sign, the force will be a repulsion force. So if we have an attraction force, the charges have opposite signs. Let's take the first case. Q is positive. The force of the test charge is directed away from Q, okay, because it's a repulsion. So if in this case the source Q is positive and the electric field is directed outward, so it has the same direction of F. So F and E, they have the same direction in this case. So every time you have a positive charge, the electric field is directed outward. Now if we take the same approach but now with a different sign, which is a negative sign, Q is negative, so the force on the tested charge is directed toward Q. It's an attraction force, okay? So in this case, the electric field is directed toward the source charge, okay? Because it's outward the pointed charge, which is the tested charge, it's toward the negative charge. So if we need to represent the electric field lines for a pointed charge, if it's a positive pointed charge, the field lines radiate outward in all the directions. Now, if you are working in three-dimensional, the distribution will be a spherical distribution, okay? So for positive charge, the lines are directed away from the source charge. That's why if we have a tested charge, the two charges will repel. The source charge Q and Q0, we will have a repulsion force. To represent the electric field lines of a negative point charge, the field lines radiate inward in all the directions, and in this case, the lines are directed from the, let's say, the test charge to the source charge Q0, and in this case, we will have an attraction, a force of attraction between the two charges. So how do we draw electric field lines? Because one of our objective, our final target is to be able to draw the electric field lines. The lines must begin on a positive charge and terminate on a negative charge. So the direction of the electric field lines is from the positive charge to the negative charge. In case of an excess of one type, let's say one has a bigger size or the magnet of the positive charge is greater than the magnet of the negative charge, a number of lines won't have an ending point, okay? So the number of lines is proportional to the magnitude or to the size of the charge. The larger the charge, the greater the number of the field lines. In our case, let's say we have the same number or the same size of charge, one positive, one negative. So the number of lines drawn leaving a positive charge will be equal to the number of lines approaching to a negative charge. Okay, so the number of lines is proportional to the magnitude of the charge. The most important properties is that you cannot, or two field lines cannot cross. Okay, so for every field, okay, we have or the field lines, they can never cross. And you need to remember that you don't have these field lines representation in real life, okay? They are like a prediction or a representation to qualify or quantify or to be able to describe the electric field. Okay, we don't find electric field lines in real life. Also, I will talk about the dipole. I think you have all seen this slide and studied this slide in the course. A quick reminder about a dipole, which will be a part, or it will be our let's say the configuration that we are going to study. So we have a positive and a negative charge. The electric field is directed from plus to minus. As you can see, that the electric field, the curvature of the electric field will increase if we go far away from the charge. The number of field lines leaving the positive charge is equal to the number of field lines terminating on the negative charge here, because in the case of dipole we have two opposite and equal charge. So if the positive charge has a magnitude of, let's say, 5 microcoulombs, plus 5 microcoulombs, the negative charge will have minus 5 microcoulombs. Okay. Another electrostatic comparison to gravity is the concept of potential energy. You all know that the gravitational potential energy, it's called U, or PA, or for French educated it's EPP. In this case it's based on the distance or the distance difference. So we need a reference point or a reference surface, which is in our case the Earth. So the position of M affect the gravitational potential energy. So it's equal to mg, which is the weight, times h. So the gravitational potential energy per unit mass, it's U, the gravitational potential energy, divided by the mass, it's a gh. As you can see, the potential is independent of the mass. So as you can see, capital M and the small m, they are at the same height h, but they don't have the same mass. Okay, so they don't have the same weight, because m is multiplied by g to obtain the weight. M has a more potential energy than small m, but they have the same potential. How do we know that they have the same potential? They are at the same potential level. Okay, so the potential is calculated by finding the ratio between the gravitational potential energy and the mass. So in case of electrical particle, the electric potential energy change if the particle moves from one place to another. So similar to the gravitational potential energy, also electrical potential energy change if the particle is moving. Okay, and as you know, to move a particle or to move an object, we need to apply a force and calculate the work. So the work done by this particle. So the work is defined by or is proportional to the variation of the potential energy. So W is equal to minus delta U. U in this case, because the work is the force times the distance. So the variation of the potential energy is the force times the distance. The force is an electrostatic force in our case, so it's Q0 E times D. Just 1 second. Times D. So in this case, the electrical potential energy U is defined by KQ0F KQ0 times Q, the source charge over R. So before discussing this part, let's do a recap. The electric force is calculating using Coulomb's law. It's K, Coulomb's constant, times Q, the source charge, Q0, the test charge, over R squared. So the force that the charges exerts on each other, it's F. As you can see here, we have two charges with the same sign. R is the distance separating the two charges. The potential energy is associated with this pair of charges or with any two pair of charges. So as you can see, U, it's K Q times Q0 over R. So what we did, we multiply the force by the distance separating the two charges. Now the electric field is again the electric force divided by the test charge. So if we take this formula and we do the division by Q0, so it's KQ divided by R squared. So it's the field, the electric field at this point. So if we replace Q0, we remove Q0, and we need to calculate the electric field at the same point. So that's the magnitude of the electric field. The potential also at this point is U divided by Q0 by the test charge, or it's E times the distance, okay, separating the point where we need to calculate the potential and Q. Okay, so that's the formula of the potential. So if we go again, as you can see, the potential is independent of the charge. Okay, so the potential at this point. So if we take the two charges, Q, small q, and capital Q, they are at the same distance from the surface, from our source charge, let's say. Q has more potential energy, capital Q has more potential energy than Q, small q, but they have the same potential V. Okay, so if we try to calculate it, as you can see here, the potential energy is a function of the charge of the source charge, let's say, but the potential is independent of this test charge. Okay, so Q, capital Q, and small q, they are at the same distance from the negative charge, okay, the negative surface, the reference point. Okay, they don't have the same potential energy because the potential energy depends on their charge, okay, but they have the same potential value, the same potential V. So the points of an electric field having the same potential, they are called equipotential points. So small q and capital Q, they are equipotential points, so they are points with the same potential. So V small q is equal to V capital Q. Okay, so in case of several points, or if we need to connect these points, they will be on the same line, what we call the equipotential line. So similar to gravitational potential, particle or points presenting the same electric potential energy are on the same potential line, or what we call equipotential line. So here VQ small equals to V capital Q. Let's take another physical quantity to define it, which is the electric potential difference. So as you can see here, in our case, they have the same potential, they are at the same distance, they are at the same equipotential lines. How can we connect different potential lines? How can we connect the potential? What is the electric potential difference? So to obtain electric potential difference delta V, we need a variation in the potential, in the electric potential. So as in little mechanics, to obtain a variation in the potential energy, gravitational potential energy, we need to apply a force, we need a work, so work must be done to remove or to move a particle, in our case to move a charge. So the potential by itself is useless. Okay, so to report the potential, also we are not able to measure only the potential. So that's why we need to define the potential difference delta V, or for example for French educated it's the tension U, and it's defined by the difference between the potential of 2 points. So the potential difference of between A and B is the potential of B minus the potential of A. So we need to move the particle from A to B. From its initial position it was A, the final position it's B. So as you can see here, the sign of delta V can be negative or positive, or if we have the same potential. When do we have the same potential? If A and B, they are at the same line. If A and B are at the same line, let's consider, let's call it another name. Let's consider C and D. So C and D, they are both at the same line, and we need to find the potential difference between C and D. They are at the same potential line, they have the same potential energy. In this case, delta V is 0. So another way or another property of equipotential lines, 2 points or particles at the same equipotential line, they have the same potential, or the potential difference of these 2 points is 0. So here you have two different representations. When we have a let's say this can be considered a road, a straight a distribution of charge through a straight line. We have a positive charge. The electric field is directed upward. Okay, it will be leaving the surface. Okay, it's perpendicular to the surface. The electric field lines, okay, they will have the same shape similar to our surface or to our source. So here the source, it's a straight line. So the equipotential lines will be lines parallel to the surface and perpendicular to the electric field. So the dotted blue lines, they are the equipotential lines, and the red lines here, they are the electric field lines. Okay, now for the pointed charge, or when we have something similar to a sphere, in this case the shape of our charge, it's a sphere or a point. So that's why the equipotential lines should have the same shape and parallel to the surface. So we will have spherical or cylindric or circular representation of the equipotential lines. If we have a three-dimensional representation, we will talk about equipotential surfaces in this case, not lines, and it will have a spherical shape. But now we will skip this part. We will consider circular lines. Okay, as you can see, we will apply the same procedures to find delta VA, delta VAB. So if A and B they have the same potential, or delta V is 0, A and B should be at the same line. Now, as the distance between the point and the source charge increases, what will happen to the potential? If you check here again the formula of the potential, the formula relating the electric potential to the distance, if R increases, the potential will decrease. So V and R, they are inversely proportional. At a certain point, we will obtain a potential value of 0. Now, another property is regarding the potential of a pointed charge. If we need to present, for example, equipotential lines with the same potential difference, and we need to obtain the same value of delta V between the lines. Okay, because it's a spherical representation, and as you can see, V is not directly proportional to R. V is inversely proportional to R. So in this case, we don't represent a lines with equidistance. Okay, so the distance separating the two consecutive lines is not the same as the potential increases, as the potential, I'm sorry, decreases, as the value in our case, because it's a positive charge, as the potential value decreases, even though we have the same potential difference. Let's say here we have plus 5, this line is 4, this one is 3 plus 3 volt, 2 volts and 1 volt. So as you can see, we have the same potential difference, electric potential difference. We have the same delta V, but of course we don't have the same R. The distance separating the these, what we call these circles, are not the same. So pay attention to this property of equipotential lines. So as you can see here, I'm representing the equipotential lines of a plate. We have a positive charged surface and a negative charged surface. As the distance from the surface increase, the electrical potential will decrease. Also, for the negative charge, it will decrease, but if you are taking the sign, it will increase until it will be 0 at a certain point, at a certain distance from the surface. So as we will have the same representation for a pointed charge. So also here, if it was a negative pointed charge, if it was that charge had a potential minus 5 volts, so it will be minus 4, minus 3, minus 2, minus 1 until reaching 0. So here I'm representing different shapes of the common or the most studied equipotential or field. As you can see here, we have a uniform representation. The direction, you know the direction of the electric field. So the electric field is always directed from positive to negative. So here we have a straight line or a plate. It's positively charged. And here we have a negative plate. So as you can see here, so it's similar to rotating these two rods and putting one in opposite to the other one. So let's consider we have the positive surface here and the negative surface here. The electric field will be directed from the positive side to the negative charge. And as you can see, the equipotential line, they are perpendicular. Keep on your mind that the equipotential line, they are parallel to the charge and they are perpendicular to the field lines. Here, because we have plates, so we will have the same separation distance between the lines. And here I'm representing the positive charge with electric field lines, and equipotential lines are the one in orange. And the configuration that we are going to study in this lab is the dipole configuration, when we have two equal but opposite charge. So as you can see, we will not obtain or we will deform the shape of the sphere, okay, as the distance between the two charges become closer. At the middle or between the two charges, the equipotential line will be a straight line. Okay, so what is the potential of this line? The potential V is 0. Delta V in this case will be half the potential. What do you mean by half the potential? Let's consider that the positive charge here, it's plus 10 volts, and here we have minus 10 volts. So the total potential difference, delta V, it's plus 10 minus 10. So the applied potential difference in our case, it's 20 volts. So here at midway, we have a potential of 0, or the potential difference in this case, it's 10 volts. So I will explain this in the experimental procedure. But you need to keep on your mind that you have a huge difference between delta V and V. So V is the potential, delta V is the potential difference. To obtain the potential difference, you need 2 points, okay? So regarding the procedure, I will be using, instead of you, a conductive paper. Okay, 2 conductive pins will be considered as electrodes or as charge. One will be connected to the positive output and one will be connected to the negative output. As you can see here, I'm using a power supply. Last week we talked about the difference between a power supply and a function generator, the difference between direct current and alternate current. So direct current, we have a constant voltage. Let's say the applied voltage is plus 20 volts. Okay, so the applied voltage between these 2 points is plus 20 volts. What does this mean? It means that the one connected to the negative output, it's minus 10 volts, and here we have plus 10 volts. Okay, one electrode is connected to the COM, the other one is connected to the volt. A voltmeter is used to measure the voltage or the potential difference. So the voltmeter should be connected in parallel. One end of the voltmeter will be fixed and the other end will be our movable probe. So I will be using the movable probe to be able to map the equipotential lines. How am I going to map the equipotential lines? Let's say here the voltmeter recorded a value of 5 volts. I will find another point with the same potential difference. So the voltmeter does not measure the potential, it measures the potential difference. So here it's delta V, not V. So it's the potential difference between plus 10 volts and this point. So I'm going to map 5 lines and give you the data of these 5 lines. These are the data that you are going to use to plot your map, to draw your map. So 5 lines and 5 electric or field lines. Okay, so let's say here the reported value, it's delta V. So it's the value recorded by the voltmeter. So we have recorded 5 lines. So here, because it's delta V, pay attention, it's delta V, not V. In the lab report, I'm asking you to write V. So V, it's simply 10 minus, let's call it Vx, the unknown value. It's equals to 4.7 volts. Delta V3 is the potential difference between the points at the straight line, the one at the middle, and the positive charge. So theoretically, it should be around 10 volts because the applied potential difference is 20. Because it's an experimental and we have what we call the sources of error. Okay, in this case, we have the line is a bit shifted. Okay, so as you can see here in the table, the reported value, as I have mentioned, it's delta V, not V. So here the potential difference is 11 or something around 10. So the potential of V3, the potential of this line is 0. The potential, you need to find the potential of V2 and also the potential of V4 and the potential of V5. If you want to prepare your map with the potential difference, please write on your map that you are considering the potential difference of these lines. So the potential difference is the difference between the positive charge and a point on the equipotential lines. Okay, so how do we do or plot or prepare your map? You will take these sets of data. As you can see, you have X and Y coordinate. These sets were recorded from the conductive paper. So the conductive paper, it has an X axis and a Y axis. So you have the X and the corresponding Y. So first you need to represent your charges, the positive one and the negative one. How do you know which one is positive and which one is negative? You need to watch the video and to see which electrode or which pin was connected to the positive output of the power supply and which one was connected to the negative output of the power supply. Now the electric field is directed from plus to minus. Before plotting the electric field, you need to let's say insert or use this data to do your graph. So you can use a paper or a graph paper, whatever you want. So for every paper, for every map, you need to specify X and Y, so your scale. So let's take the first point. Y is 3 and X is 28. So let's consider here, you need to, depending on your scale, let's consider that is the right scale. It's the first point, second point, third, and here are the 5 points of the first step. Okay, you will repeat the same procedure to plot the 5 lines. Then to draw the equipotential lines, don't dot to dot your lines, okay, or don't join your lines. Using a pencil or by hand, simply do a curve which is the best fitting or the closest line to all the points. So that will be V1 with its value, or simply delta V1 with the value reported here in the table, 4.5, 4.7 volts. Okay, you represent 5 lines. Okay, then you need to represent 5 electric field lines. Let's say here it's our positive charge, here it's our negative charge. It's from plus to minus. So as you can see, two equipotential lines, they cannot cross because they don't have the same potential. Okay, two lines to cross, they need to have the same potential. Okay, so that's why two equipotential lines, they cannot cross. Also electric field, two electric fields, they cannot cross. So you need to plot 5 electric fields, specify the direction using the arrow, so it's from plus to minus, and to add that the electric field and the equipotential lines, they are perpendicular. So don't forget the title of this sketch. Okay, every time you are going to do a sketch or a representation, a graph, okay, you need to add a title, a scale, the direction of the electric field, the values of the potential difference or the potential, where is your positive charge, your negative charge, all your points. So everything should be added to the map. Now also in this lab experiment or in this lab report, you don't have a calculation part. So you don't have an error or to report a measured value. So it's more conceptual, based on the course and what you watch on the video. And based on this presentation, you need, let me check the question. You need to, in your lab report, you need to fill the question, answer the question, do the description, all the descriptions, where the So as you can see here, you will copy the data, fill the table, and then based on these data, you will prepare your graph, and don't forget to add your graph to the report, and then you will answer these questions. Question number 1, you will describe and explain what you have obtained. Also, you will answer the question regarding if two equipotential lines or two electric field lines can cross. You need to sketch the parallel plate configuration. We did not study the parallel plate configuration in an experimental way, but I have already explained it during the theoretical background. Also, you need to answer all these questions. Every time you need to do a sketch. Don't forget the title. Don't forget to precise if you have a positive or a negative charge. Don't forget to add the direction of the electric field. And every time I mentioned or I asked you to explain, you need to clarify, or based on your sketch, to explain what do we have, the direction, and what is the direction of the electric field. Why do the equipotential line have this shape? Okay, and that's it. As you can see here, you don't have an error calculation, no significant figures also in this lab report, no rounding. Okay, so that's it. If you are skipping the live session, please watch this video and let me know if you have any question.